Hello everybody, good morning. Welcome all to FHIR Profiling Overview. If you're expecting a different presentation, now's the time to move. Otherwise we're going to get started. This will be a very intense presentation. I have a lot of slides. I hope you all have some coffee, but it's going to be fast-paced. So prepare, brace yourselves. Here we're going. A little introduction. My name is Michel Rutten. I work for FHIR in Amsterdam. Well, I've been writing software on an old 8-bit machine since I was a small kid, working in Microsoft technology, well, all my professional career, so it's a privilege to be here. Thank you, Microsoft, for offering this great location. And I joined the FHIR team about 5 years ago when FHIR was at the DST1 phase, and I specialize in profiling. I'm the lead developer of Forge. That's a FHIR profiling tool, a profile editor. So if you use that tool and you have any issues, you know who to talk to. That's me. Well, let's get started. These are the topics I want to discuss. It's quite a lot. Profiling is a broad topic. I'm just going to give a global overview. I'm not going to do any demos. This will just be a broad introduction to the different aspects of profiling. So we're going to discuss first the motivation. Why do we actually do profiling? Why do we need this? I'm going to show you what the parts are of the conformance layer in FHIR, what FHIR provides to do profiling. Then we're going to move into profiles themselves, extensions, as Simone already discussed this morning. I want to talk a little bit about packages, a distribution mechanism for your profiles. And then implementation guides, that's how you actually bring it to the developer. And at the end, the registry, that's where you can publish your profiles so they're discoverable and everybody can find them. So a lot to cover. So the need for profiling. Why do we need profiling? Well, FHIR is a platform specification. It provides you with a set of about 140 resources now in Release 4. They've been harmonized by doctors worldwide. They provide the common functionality that's common all over the world. But usually within your nation, you need to adapt that because what FHIR provides out of the box doesn't completely fit your use case. And that's why there's an additional layer of profiling that allows you to author these differences. So you have a single set of resources and you adapt them to your context of use. And that's why profiling is there in FHIR. So a part of a profile, you describe which resources do I use in my use case? Which are the elements that are important in my use case? Which API features do I use? Operations, search, for example. Terminology you can express, a very important part of your profile. And also how to map these profiles to your local requirements. That's all part of a profile. And the key thing that FHIR introduces, because we had profiles in V2 and V3, what FHIR has done is to make that all structured. You can describe that in a narrative. You can do a profile in a PDF document, but that's not computable. And FHIR provides you with a way of expressing all these constraints in a computable way, so we can feed it to a machine and reason about it, which is very powerful. And it's independent of the serialization format. FHIR has XML and JSON, but this is an abstract technology that works on a conceptual level. You can publish them. You can validate them. You can generate code. You can generate a UI. And that's all possible because it's computable. That's a recurring theme in this presentation. It's structured and it's computable. So let's take a look at the parts of the conformance layer. If you go to the homepage of the FHIR spec, you will see that the resources, they're divided into groups, and one of those groups is the conformance group. You can find it on the resource overview. And these are the main resources that are part of profiling. So we have some resources that are for describing content, structure definition, that's really the key part that allows you to describe a resource or a profile on a resource. And a structure definition is actually a list of element definitions. You have something like a graph definition for querying. Then there's a set of resources focused at terminology, value set being the key part, where you pull in terminology from different coding systems and apply that to an element, make a binding. We have some resources that are focused at describing your operations. So which operations does your server provide? Can I get a patient? Can I update a patient, for example? Is that allowed? You can describe that, again, in a computable way. You can describe your search parameters. On my server, you can search patient by last name, for example. And there's a structure map that allows you to author mappings between different resources or profiles. And there's also some additional, miscellaneous resources. We have a capability statement that allows a server to express its capabilities, again, in a computable way. There's a resource implementation guide. It's optional, but you can use it to even generate these implementation guides in a computable way, or by means of code generation, for example. And there are two resources that are focused at testing. So there's also, you can have a FHIR test server, and you can have your server implemented and then run a set of unit tests. And test script and test report are focused at this. The key is structure definition. That's the main part of this presentation. So this is like the DNA of FHIR. It's how you express your data types, for example, an address or a human name. It's how you express a resource. For example, a patient is defined by means of a structure definition or an observation. And it also allows you to profile these resources and to describe your constraints, also by means of a structure definition. So it's a set of constraints on these resources and data types. And you can also describe a new element. If you need to add an element to patient, then you need to describe that. You do that by means of a structure definition. And there's even an application called logical models where you can create these structures that are not directly mapped onto FHIR, but there's on a higher advanced level. I won't discuss it in this presentation, but maybe get back to it when you ask some questions. So what does it allow you? Because it's computable. Because it's computable, you can compare them. You can write code to look at two structure definitions and list the differences. That's what the FHIR spec actually does. You can transform them. You can validate them. Here's an instance data. It claims to be conforming to your profile. Is it actually true? Because it's structured, you can write some code to make sure to verify this compliance. And you can generate code and you can generate a UI. And that's all possible because it's computable. And the operation definition, as I mentioned, that allows you to express the operations that your server provides. There's a lot of operations out of the box, but for your implementation, you might just need a couple, and you might add your own operation, maybe a custom financial operation or something. You can describe that, again, in a computable way. What's the input parameters? What do I get back? What's the behavior of that operation? What resources does this operation work on? So you can extend the FHIR API with your own custom operations. And the search parameter, you can define your own searches. If you add an extension, then out of the box, FHIR can't search that extension. So then you can author a search parameter that says you can search in this new field that I added. And again, you can express it in a computable way. So what's the name of this search parameter? Which resources am I searching on? For example, this is searching on patient. And which elements does it actually look into? And again, it allows you to extend the FHIR API with your custom searches in a computable way. So we can reason about it and discover these searches. Capability statement kind of ties it all together. A capability statement is published by a server, and that's a way for a server to advertise its capabilities in a computable way. So a client, on the first request to a server, it gets a capability statement, and then a client can dynamically disable or enable certain features in the UI depending on the capabilities of that server it's connected to. So this is very useful in a dynamic situation where you don't know the clients you're talking to, and they will vary. So you have discoverability. And it ties in all the other conformance resources. So a capability statement will have a list of structure definitions saying this is what I support, these profiles. It has a list of operations saying these operations. Search parameters are in there. Serialization formats, you might just say my server only does JSON, I don't do XML, you can express that. And again, it's all in a computable way, so it's discoverable. You can write code that adapts itself depending on the statement. Structure map is fairly new. It is a little bit of a lower maturity level, it's still being developed, but it allows you to map one structure to another. So that's very useful if you need to map, for example, legacy standards onto FHIR. Or you can also use it to map a logical model onto a set of concrete FHIR resources. And again, you can do it in a computable way. So you can write, well, a server that knows how to execute these mappings, and you can send the mapping to the server and it will transform the instance. And that's actually tied into a FHIR mapping language, which is a separate specification that's part of FHIR. You can find it on the FHIR spec. Computable, again. And finally, this implementation guide. As I mentioned, you can write an implementation guide just by providing a narrative and writing it in Word, but sometimes it makes sense to use all this computable infrastructure of FHIR that you have in place already. And then by authoring an implementation guide, again, it becomes computable. So it contains the narrative, which is not computable, but it does also contain a list of profiles and a list of operations, so you can look into that implementation guide and actually do some code. There are tooling by the FHIR community, like the IG publisher, that actually knows how to handle these implementation guide resources. And compile them into a website. And that's actually the way that the FHIR spec itself is being made. And can use it to validate. So again, because it's computable. Here you can see this is a little UML diagram I pulled from the FHIR spec, and it shows you how these resources relate. So the capability statement, that's how the server expresses its capabilities. It references all the other resources, and also the implementation guide, which is a documentation for the developer. You can find this on the FHIR spec in the conformance module, this UML diagram. And these resources are actually used by the core spec. So how is a FHIR patient resource defined? By means of a FHIR structure definition. FHIR is built upon itself. The core data types like human name, codable concept, address, they're all defined by means of a structure definition. Same for these 140 resources. The FHIR spec publishes these structure definitions that describe these resources, elements, data types, bindings. And also the default REST operations that the server provides. Out of the box, you can get a patient, you can update a patient, you can put it, that's all documented. So the FHIR spec contains a lot of these conformance resources that describe the spec itself. So you can see, it's kind of a bootstrap. It's like a picture from the Baron von Munchausen where he pulls himself from the swamp on his boots. FHIR is built upon its own, it uses the spec to define itself, like a compiler that compiles itself. And also that allowed us, because we eat our own dog food, and because of this feedback loop that allows us to increase the maturity level of these structure definitions, because it took a little while to come to this level. And by using it in the FHIR spec at DSTU1, we discovered like it's not there yet. We need to add some elements, change some elements, and that actually drove structure definition to a maturity level 5. So this is normative now. And by using it in the FHIR spec, we made sure that it's pretty powerful and we can do everything we need. A little sheet I put in between. Conformance resources are a little bit special in the way you identify them. All resources in FHIR have a resource ID, but that's server assigned. And if I push the same structure definition to 3 different servers, I will get 3 different resource ID. The server assigns it. But I need a way to make sure that's actually the same profile. So all these conformance resources have an additional identifier called the canonical URL. You as an author assign that, and usually you will use your company domain in that, so you own that URL. And all copies of that profile or operation definition or search parameter will all have the same canonical URL. So now you can have a reliable discoverability because the copies will all be the same. So anytime you have a reference to a conformance resource, it's always based on a canonical URL. URL, it's encouraged to put up a website at that address. If you own the domain, you can actually do that because a developer, when they get a URL, they will paste it in a browser, and it's nice if it resolves. It's not necessary. FHIR only relies on the URI aspect, so it has to be a unique resource identifier. It has to be unique. Otherwise, there's confusion between profiles. But it's encouraged to actually make it a URL and put up a website. And that's what the FHIR spec does. So if you take the canonical URL of the patient, hl7.org/FHIR/structure definition/patient, paste it in your browser, and you will hit the spec, and it'll show you the description of the patient. And that's really convenient for a developer. It's not mandatory, but it's encouraged. So you can try this out. And here's a little example where you made, for example, a profile saying, this is my profile on a special custom patient. I'm going to push it to 3 different servers. All the servers will assign a random ID depending on what the server decides, but they will all share the same canonical URL as you see in the top of the diagram. So for conformance resources, you don't use the resource ID, you use the canonical URL. Let's go into profiles. So what is a profile? It's the term is kind of heavily overloaded with an HL7 spec. But within FHIR, I always use the term profile to describe a set of constraints on a data type, set of constraints on a resource, set of constraints on another profile, because you can have layers of these. Be aware that sometimes people will use the term profile, but they will actually mean an implementation guide. That's the way the term profile was used in the V2 or V3 world. So depending on your audience and who you're talking to, make sure that you're both on the same page about that use of the term profile. Within FHIR, I always use the narrow definition. For me, a profile is just a set of constraints on a single data type or a resource. Maybe a little trick question, because these data types and resources are all defined by means of a structure definition. So what's the difference between a data type and a resource? Raise your hands, anybody. You must know, Brian. No? Please.
Data type cannot stand on its own.
Exactly. So a data type is always part of a resource. You can't push an address to a server. An address is always part of a patient. And then you get that patient back from the server, and the patient has an ID. There's no way of an address having an ID. It always belongs to something. So data types are always components of a resource. By all other aspects, they're exactly the same. But they can't stand on themselves on a server. They're always part of a resource. So that's the difference. As I mentioned, sometimes we'll use the term profile in a loose way. And you can see that disappearing in the FHIR spec, actually. But talking to V2 people, make sure that you're on the same page. Next. About layering, as I mentioned, you can profile a FHIR resource, you can profile a FHIR data type, but you can also profile somebody else's profile. So you have profiles on profiles. And that makes sense if you look at an application. You can see the FHIR spec provides very broad set of resources, and then you can start constraining them on a national level. For example, for the US, you can add some specific mandatory elements that are not in the spec, but that are required within a national region. And from there, you can specialize further down. For example, in Norway, they have 3 different regions, and they're not completely harmonized. So they do have national profiles, but within the regions, they specialize them further, depending on their way of their workflows and the procedures. And then within an organization, you can even take these profiles and further specialize them, for example, for different divisions within a hospital or within a vendor. So you have these layered profiles. And every profile inherits all the constraints from its parent. And as the set of constraints become larger, of course, the set of instances that match these constraints becomes smaller. And eventually, it is even possible to write a profile where no instance can ever match. But that's like a SQL query saying, select star where 1 equals 0. That's a valid SQL query, and you will always get 0 records. So in a way, you could look at a profile as a where clause, as a predicate, as a filter. So structure definition. This is the core of conformance resource. Well, first of all, it has some metadata. Canonical URL. All the conformance resources have this canonical URL that uniquely identifies the profile. It has a name and a title. So the name is for code generation, no spaces, etc. The title is more of a human-friendly display name. You have a status saying, I'm still working on this profile, we're in draft, and then once it's finalized, you bump that status to active. It has a date. It has an author-assigned version that you can use within your workflow. You can add some information about the publisher, contact information, so when people find that profile, they know who to talk to when they have feedback or comments. And it refers to the base profile, saying this is a profile on patient, or this is a profile on observation, or this is a profile on somebody else's patient. And then in addition to this metadata, it has a list of element definitions describing all the elements of, for example, a resource. So that will say this is patient.name, and that's patient.address, and that's patient.communication, etc. And all these elements will be described by means of an element definition. And the element definition gives you the name of the element, the cardinality, is it repeating, the data type, like a string or a codable concept or an address. And then you can add terminology bindings on there, even complex constraints, mappings to other specifications. You can map to V2 or to the RIM. And you can even add some default or fixed values. And there's a couple of narrative fields that allow you to comment and describe that element. And you can display it in a user interface. Element definition is a data type, by the way. It's always part of a structure definition. That doesn't exist on itself. Complex constraints, I won't go in very deeply to it, but these are ways of saying when that Boolean is true, you're not allowed to enter that field. Or if you select this code, then you should add, or you should fill in that element. So there are constraints that are touching on multiple elements. And you need kind of a query language to do that. Initially, FHIR tried to use XPath, but that's really not a good fit. FHIR tries to be independent of the serialization format. XPath only works on XML, so what you're going to do with JSON or RDF or protobuf, that's hard. And also these expressions got very wieldy. Something like slicing it's hard to express in XPath, so the expressions became really large and nobody could read them anymore, and just a couple of people could author them. So eventually the community decided that there had to be a query language on a conceptual level, independent of the serialization format, and that's how FHIRPath was, well, invented. So it's introduced in DS2.2, and it's independent of the format. You can see some examples here. It's kind of inspired by a fluent syntax, like maybe you know link queries in .NET language. That's kind of how we try to model a language. And you can see some examples here. And you can add your own complex constraints to a profile. You don't need to. This is a little bit more advanced, but you can author these expressions. And there are interpreters and compilers provided by the community for the big languages in Java and C# and even JavaScript, for example. And there are testing tools that allow you to write these expressions. And it's also used by the HL7 canonical quality language, CQL. So FHIRPath appears in both these technologies. So it's related to FHIR, but it is a separate spec. So how do you refer to a profile? Here you see an example of, let's suppose I made an observation resource. This is actually an instance that's been exchanged on the wire. So this describes an actual observation that's been taken place, maybe on me, a cholesterol measure. Now you can put a tag on that instance saying, I conform to a special observation profile. And it uses the canonical URL to refer to that profile, because that uniquely identifies that profile. Now, of course, this is just a claim. And a claim you have to verify. So when you publish that instance to a server, the server can read that tag, use that to resolve the profile from its internal database, or maybe even go out on the internet and fetch that profile from a registry, and then perform a validation. So you claim to conform to that special LDL cholesterol observation, but I'm going to verify and make sure that you actually do. So you perform a validation. Again, this is possible because it's all computable. And here in this example, initially you try to fetch it from maybe your internal database, but if that doesn't resolve, then you could reach out to, for example, simplifier.net, which is a global profile registry. And you could even pull them in remotely by using that unique canonical URL. Oh. So a little about versioning. FHIR has very well-defined rules for versioning, because breaking changes, they hurt everybody. They break your implementation. So FHIR says if you fix a typo in a profile, that's not a breaking change. That's okay. You can keep the version at the same number. But once you introduce a breaking change to a profile that you published, that people actually started implementing, then FHIR says you have to bump that version. You have to bump the major version to convey to everybody, I made a breaking change, and you have to adapt your implementation. And what is a breaking change? Well, it kind of depends. Only you as an author know that. Not everything. Well, 90% you can express in a computable way, but there's always this behavioral stuff that maybe you can express. So you as an author decide what is a breaking change. And if all existing data still validates through your new profile, then it's not a breaking change. And then you can maintain the same canonical URL. But if you introduce a breaking change, then you have to make sure that people don't get confused. And if an existing server is still hitting that same canonical URL, but it's now getting a new version of the profile with the breaking change, then that implementation will break. So now you're supposed to assign a new identifier. And you can number it, you can add a v2 to it, for example. That's usually what you will see. Add a version number to the canonical URL, and they can coexist at the same time. And then existing implementations can slowly move to the new profile until after a while, maybe you can see that the old one isn't used anymore, and then you can retract it. So a published profile, you should consider it as a promise forever and ever and ever and ever. Once you put out a profile with status active, saying this is final, you should assume that people start building clients and servers based on that profile, and then you really shouldn't tinker with it anymore. You really shouldn't introduce any breaking changes anymore, because you will get phone calls. So it's an eternal contract. Of course, the status field you can use, as long as the status says draft, that's an indication to you that the team behind this profile is still working on it. They're still discussing it, and then it's still moving. So you can start implementing a draft profile, but be aware, this might change while they're still working towards an active version. So a little bit of a technical sheet. If you go into the structure definition, I mentioned it has a list of element definitions. Well, actually it has two lists of elements definition. One is called the differential, and the other one is called the snapshot. The snapshot, that's the fully expanded list of elements that describes everything. But there's a lot of redundancy in there, because usually you will inherit a lot of elements from the base profile, from your patient, and you just constrain 2 or 3 elements. The differential only describes these modifications. And usually as an author, you're only interested in a differential. You want to know, what did you change with respect to that standard FHIR patient? You added an extension. That's what I'm interested in. And the differential just zooms in on these differences, and you can present that in the UI. The snapshot, on the other hand, that's useful for the server, because it has to validate, and then it needs all the elements. So the snapshot actually aggregates constraints from all the base profiles down to your profile and expands that full list. You don't need to exchange the snapshot, because it's a couple of megabytes large, and the differential will be maybe 100 kilobytes, depending on how many constraints you add. Most FHIR servers have the capability of generating that snapshot out of the box. So you can just publish a structure definition with a differential, and if it's a smart server, it knows how to expand it into a snapshot, and then it can use it. However, if a server doesn't have that capability, then you can generate the snapshot manually on your machine and publish that to the server. And there are snapshot generator components for Java and for .NET available, so you don't have to write it themselves. It's actually pretty hard. But it's all in place. So authoring profiles. How do you author a profile? Well, initially 5 years ago we didn't have any tooling. So the FHIR spec started by people writing XML or JSON by hand using Oxygen or just a text editor, and that's really, really painful. Once the list of elements becomes larger and larger, and the structure of the XML is not always easy to read, it's very easy to change the order of elements, and that breaks the profile because FHIR is ordered. So it's painful to do this by hand, and you really don't want to. But fortunately, there are tools. Well, it started out initially, the FHIR spec used an Excel sheet to do this. That was like the first attempt, but it's hard. It's a flattened list, and it doesn't really map to a tree because that's nested. So that's, again, it's painful. So don't do that. But we have professional tools. Lantana is a company specialized in profiling. They've been working in this space for a long time. They have a tool called Trifolia. It's actually not FHIR specific. You can also create V2 profiles, for example, but it completely supports FHIR. And that's a web-based application. You can get an account there by going to this address, and you can use that to author your profiles. That's a point-and-click interface. If you like UML, there's a specialized tool made by Dave Carlson. I think he's here. I noticed him entering, so you can talk to him if you want to. And he's been working on this tool for a long time. Again, this has a history from V2 and V3. And the MDHT tool, in the MDHT tool, you describe your constraints in UML, and then it compiles that into a certain technology, like, for example, FHIR. It's a Java-based project. I think it's open source. And if you go to the URL, you can find a description of it. And then also there's a FHIR-specific tool. This is the tool that I make. Forge it started out as a reference implementation, and that's an editor for structure definition. So Forge doesn't do older technology. It doesn't do V2 or V3. Forge is specifically for FHIR. It's a Windows desktop application. It's not open source, but you can download it for free from our website. And especially if you want to get into profiling, I think this is an easy way of doing it because it provides a graphical user interface, and you can take it from there. So it's also a nice learning tool of discovering what's in a structure definition, or opening, like a viewer, you can open up a profile, it will present to you in a nice graphical way. And I try to validate, so once you start adding constraints, the tool tries to inspect what you do, and if something doesn't seem sound, it will give you a little warning saying, well, the FHIR spec doesn't allow you to do that. So it tries to help you to put out a valid profile. Well, let's talk a little bit about extensions. So usually out of the box, the resource isn't completely sufficient to your needs. Patient is a great example. In the United States, it's mandatory to administer patient race and patient ethnicity. In Europe, where we're from, it's forbidden to administer these fields. So you can't put them in the FHIR spec because they're opposing constraints. So for race and ethnicity, the US introduced their own national extensions to express that. And then they made a national US patient profile that made these two elements mandatory. So you need to define extensions. Hey, that's a bit fast. So as I mentioned, how do you find an extension? Well, a simple extension will have a single field, but there might be multiple fields. You might have a geolocation with an X and a Y coordinate, so you can do a complex element. And it's defined by a structure-defined resource, the same as the data types, the same as the resources, the same as the profiles. Again, it's identified by means of a canonical URL, so everybody can refer to your extension in a non-ambiguous way. And it defines the context, saying, well, this patient race, you can only put that on a patient resource. It doesn't make any sense to put it on an observation. So you can limit the applications of your extension, saying it's only useful for these data types or for these resources. But you can reuse an extension in different profiles. For example, you can imagine that maybe race and ethnicity, you could also put it on a person resource or maybe on a practitioner resource in a way. So an extension doesn't have to tie into a single resource. It could have multiple applications. Out of the box, FHIR allows extensions on all elements, even on primitives. So you could put an extension on the root of a patient, you can put an extension on patient.name or patient.name.family. You could even put an extension on a Boolean value. That's really hardcore and it's not something that I would suggest to do, but if you need it, you can, and you can create a special flag on your Boolean saying this is true, but with some extra information. And it's still valid. So out of the box, a FHIR patient, a core FHIR patient can have extensions on all the elements, Maybe in your use case, you can't handle that, and you want to constrain that down, and that's possible. You can constrain down these lists of extensions, saying in my use case, these are the extensions I expect, they're mandatory, don't send me any other extensions because I'm not capable of processing them. So you can lock that down. And you can see the element definition refers to the extension, again, by means of the canonical URL of the extension definition. Anytime you refer to a conformance resource, you use that canonical URL. So here's an example. That's a Dutch patient, Irma. I know people working in HL7 space might know her. She's from the patient working group. And this is her Dutch patient profile. You can see there's a nationality that we added. That's not a part of the out-of-the-box patient, so we have an extension for that. And you can see Irma's instance conforms to the patient profile. And then in Holland, we made a special Dutch patient profile that includes that nationality extension. You can see that the patient profile in Holland refers to that patient nationality extension definition. So now, if I send that instance to a server, by using these two structure definitions, it knows what I'm sending. And the same way, you can add multiple extensions. And you can see, again, the reference is based on the canonical URL of that patient nationality. And this is an example of a complex extension because it has two different fields. It has a code and also a period because people might move. And say Irma was based in Holland between 2000 and 2018. So there's two elements in this extension. Oh. So most extensions are primitive extensions. FHIR out of the box even provides you with a large set of extensions. For example, nationality, that's something that's provided by the FHIR spec. It's not part of patient, but there is a standard extension to do this. And most of the extensions are primitives. They just have a single field with a single data type. For example, patient birthplace, patient birth time. It's just a single field. But it is possible to author a complex extension, as we noticed with nationality, and then you can have even nested fields. And you could have an extension that have a lot of nested fields. I would advise you to keep the complexity down and not go further than 3 nesting levels, because usually you want to break it apart and promote reuse. Typically, an extension will have a single field. You have some of them will have 2 or 3 fields. That's what you will see in the wild. A little bit of packages, because hefty fast, 5 minutes left. So you make these profiles. Now you want to distribute them to different machines, and the server needs to get these profiles. Well, as we noticed, a profile doesn't stand on its own. A profile references extensions, and that implementation guide that references operation definitions and server parameters. And in your use case, they all belong together. So initially, we publish these resources one by one, and then you have to get them one by one. But it makes much more sense to put them in like a package and saying, this is my use case, and everything you need is inside this. So conceptually related FHIR resources, you want to bundle them and publish them as a coherent set. Well, instead of inventing our own technology, it was very similar to, well, what we do as developers. We have package management in Java and .NET and different programming languages, and there are technologies in place. So FHIR didn't reinvent the wheel. The community decided, let's use NPM standard. It's widely adopted, there's a lot of tools available, and it fits our needs. So you have this notion of a FHIR NPM package where you bundle your profiles, you zip it, you publish it to an NPM server, and then everybody can search on it and get everything that's related. And you don't have to find all the different extensions and all the operation definition if it's just a single file. And it's versioned. It says, this is version 1 of my package. Start building. Next year, I'm going to publish version 2. Some parts will have changed. And it gives you a version management tool. So packages can depend on each other, just like these implementation guides. You say within your company, well, I'm based on national profiles, and they're based on the FHIR spec. So these packages can point up. And the package manager is smart. If you get a package, it will resolve the dependency graph and download everything onto your machine. So it's just a single click. And resolves up. And then the server gets everything on your machine. Oh. So you can publish these. We actually integrated a package server in our simple FHIR registry. So you can upload and publish these packages, and they're discoverable. There's a search engine in there. There's a web interface, so you can search by keywords. But there's also an NPM API. So when you have any NPM client, you can point it to this URL and it can fetch these packages for you. And recently, I also integrated a very simple package client into Forge, the profiling editor, because when you're inside of the tool, you really don't want to reach out to a website and download it, so it's convenient. Now you can switch to the package manager, you search by keyword, you can push add, and immediately these extensions are available to you. So that's in a couple of seconds, you will have new functionality. A little bit of implementation guides. As I mentioned, you can write a narrative in a Word document, but we have this resource in place, and it provides a little bit of power because it's computable. So the resource contains a list of Markdown pages or HTML pages. That's not computable, that's formatted text. That's intended for people, for humans. But it also refers to conformance resources, and this is a part of the IG that's more meant to be computable. That's intended to be processed by computers. And both of them are tied together in that implementation guide. Packages were invented later than the implementation guide, and then we said, well, it makes sense to refer to the package from the IG. So if you look at the latest version of the implementation guide resource, it actually says, well, here are the narratives, this is how you build my use case, and then download these packages to make sure that you comply. So it's all integrated. Well, how do you create them? You can write them manually, generate them from simple FHIR. The nice thing about, because it's computable, is you can exchange them. So because it's a FHIR resource, you can actually publish it to any FHIR server, and then you can transfer your implementation guide to a different machine. And that machine can use the IG to validate the resources that are exchanged on the wire. So you can imagine by uploading the implementation guide, the server will get that package out because that's what the server needs. It doesn't care about the narrative, that's for the developer, but it gets that package. It could install it in its own database, And once it's finished, now the server is capable of processing these special instances that conform to these profiles. And some servers are smart enough to do it dynamically. So for example, the server created by my colleague Christian, the Vonk server, you can actually do this. You can upload a profile. If you're authorized, the administrator needs special permissions to do that for a special endpoint. And then 2 seconds later, the functionality is in place. Or you can upload a search parameter, and then the server will look at that because it's computable. It knows what to do. It starts building an index, and when the index is ready, a couple of seconds later, now you can start searching. You don't have to reboot. That's pretty powerful. As I mentioned, this is part of the IG is focused at humans, and part of the IG is focused at machines, and it ties it all together. So everything is in there. It's the complete set that is needed to implement your use case. If you give this to the developer, he shouldn't really have to call you anymore. You should have all the information necessary to build the use case. There is an open source tool by the FHIR community, the IG Builder, is a command line tool. So it's powerful because you integrate it in a script, but it's also pretty hard to use. It gives you back sometimes a stack dump or these exceptions. So it's a little bit of a struggle to make that work. Once you got it working, it's pretty powerful because it's all code generated, but it's not very user-friendly. There's also some online editors. We started building a simple, like web-based IG editor in Simplifier because I just want to keep modelers away from the XML and the JSON and the Markdown. You just want to point and click and focus on your, well, on your domain. And I think there's also some efforts going on within the community to create different tools, and they might, well, check the Zulip. There's a special stream on implementation guides, and maybe soon somebody's going to announce that a new tool is available. I know people have been working on this. And you can, on Simplifier, if you go there, you can find some examples of IG. If you want to know how it looks, for example, the Germans made a national implementation guide. They published it on Simplifier, and that can be like an inspiration for you. Like well, what's the typical content of an IG? It's a different topic, but something. I came from CMS World, actually, and you can see these different workflows. You have an authoring workflow where it just, within your team, you have different revisions, and then finally you say, okay, now we're going to go final, and you publish it. And there's a separate publishing workflow there, because maybe in a couple of years you're going to announce a new version, and then a couple of years later you're going to retract that original one, saying it's now being deprecated with special rules on it. So there are two workflows. And this is actually, you can create tools that support that. I'm running out of time. A little bit at the registry. There's an HL7 registry. That's for official profiles, but it's actually being fed by Simplifier. So everybody can publish these profiles as Simplifier, and then if you want these profiles to also be discoverable on the official HL7 registry, you just check a box and it appears there. And you as an author determine when it's ready. It's more, Simplifier also contains a lot of experiments and drafts, and people are just playing around with FHIR, and it's perfectly fine. Create a test account and just, publish something, keep a draft. While the HL7 registry is intended to contain only final published profiles. But it's a subset of the Simplifier database. And feel free to start putting some examples on here. So because it's all computable, it's pretty powerful. Once you upload that profile, it's a FHIR server. You upload an example instance and you can validate it. And the registry actually allows you to see, if you publish an extension to a global registry, once people start using the extension, the registry can see these incoming references. So in a couple of months, you can return to that website and you can ask for statistics, and then you will see how many people in the world adopted your extension. That's pretty powerful. And here you can see an example of the online implementation guide editor, where you can enter some Markdown, and we have special instructions to render those trees, so you don't need to do it by hand. The system just pulls it from the database, and it knows how to display a structure. So you don't have to write all the yucky LEUL HTML. It does it for you. That's it. I ran out of time. There's a lot more to discuss. So after this session, I'll be going to McKinley. I'll be there for about an hour. I'll be ready for your questions. You probably will have one. We don't have time for it. Also, tomorrow at 10:15, my colleague Ardon is giving a Let's Build My First Profile session. So then we'll get hands-on, and we'll start playing with the tools. Well, there's no time for questions, unfortunately, so thank you.